Where can I find my foam in Alaska? Big question. What you want to do, Alaska, is called Dow Chemical. They have an 800 number, and it's 800-232-2436. And the extensions that you can start with would be 1275, extension 1268, and if all fails, ask for customer service, get an operator. Dow will give you the local distributor. He might be 40 miles away, but at least that's the number to start with. Keep in mind, depending on the foam you're looking for, and we'll talk a little more about this, building supply houses, look under your yellow pages under insulation. That's one area to find foam distributors. Keep in mind that this... Number again? Oh, okay, number again, 800. Boy, we've got some slow ones this morning. 232-2436. Extension 1275 and extension 1268.
Ron, you can also tell that we have blue foam over there at our shop.
By the way, Mike has blue foam in his shop. Mike will not let me forget that, okay?
Negotiate your best price.
There you go. Yeah, negotiate today, guys. Okay, so we're talking about foam, where you find it. Under insulation, some of the foams here, a little more down and dirty grades, you can get it at your building supply house. Quality will vary there, and we'll get into some of those details. Mainly, you're talking about two kinds of foam in the way the foam is made, the way it's constructed. You have what is called EPS, expanded polystyrene. That's your typical beer cooler foam. The little coffee cups that you're drinking out of out here. Literally, the way that EPS, expanded, as the name says, expanded polystyrene, the manufacturer starts out with small pellets. And they look like pretty much the pellet that you see in the final product. You know, when you break styrene, the expanded beads, you see a bead structure. Imagine that you took a big cardboard box. Now, of course, they have big, huge metal molds. And you fill that with small pellets up so far. And you close the box and you injected steam and it expanded to fill the box. That's how this is made, depending on the bead size and formulation, the amount of beads they put in, and the dwell time of the steam injection. This is what you get. You'll find some with large-looking beads, some with small-looking beads, and they formulate that for various applications. So you aren't going to have a lot of choice when you start buying your foam, and I would say don't worry about it too much. The physical properties are close enough for your purposes. One thing, though, and this can cause trouble with cutting foam, I said inject steam. When these blocks come out of the mold, they're dripping wet. And every manufacturer, if he's a good manufacturer, has to let that block sit there for 30 days. And of course, in Louisiana, or where was that, Houston, it's probably got to sit there longer for the moisture to evaporate out. Sometimes you can be cutting a foam core, and now I'm specifically talking the white foam, and you'll get the strangest thing at one end of the wing you're cutting. The foam, the beads are different. It erodes away severely differently. And what you find is that's at the edge of the block, not so much the physical composition of the block, but moisture. It hasn't cured fully. So that's one little caveat that you want to remember when you're cutting the expanded styrene. Generally, your density is 1 pound. One very important factor, these foams are built for, generally, construction purposes, not built for the modelers. Not even 5%. Like balsa, is built for you guys. So the one thing you need to remember, the only criterion that this is made to is that does it meet building standards. That has nothing to do with generally the physical, the chemical properties or the density throughout the block, or because what you're going to find is when you cut foam, you'll run into funny things, whether it be blue foam or the expanded foam. And Dow will tell you right up front, look, we build it to building code standards, and there's a wide latitude in the physical properties if you start looking at it on a micro basis. Generally, though, as we all know, it's a great medium to work with, but just understand you can run into funny problems. Recycle foam. When you go to Builders Emporium or some places where you buy the down and dirty white foam, it's a recycle foam. There could be trash in there. Bottom line, though, it's cheap enough to go ahead and buy it so you mess up a wing or two. Don't worry about it. But virgin foam is what you would buy through a distributor and through most of your of the Builders Emporium type places. White foam, I mentioned about the 1 pound density. It's easy to cut. Interesting, I find that I like to cut it at a little higher temperature than the blue foams. And I think that has to do with the fact that we're looking at these cells and there are voids in this foam. You have a little less conduction of the heat to cut it. So I find I have better success if I tweak the heat up a tad more on the white foam. The other type of foam, blue foam, extruded. Toothpaste, every morning you squeeze that tube, out comes the toothpaste. That's the way this foam is made. Depending on the particular blocks and the physical properties they're trying to acquire, it may be a block that's extruded that's 16 inches by 3 inches, or it could be larger depending on what the manufacturer is trying to accomplish. Density in round numbers runs from 1 pound plus. Yeah, you can get some less than 2 pounds. We all think of the blue foam, 2 pound foam. But no, there are some of the extruded foams that are less than 2 pounds. Now, generally, 6 pounds becomes the commercial available limit. And there's a sophisticated technology to get it that dense, and Dow Chemical is the only one that makes the 6 pound foam. The one thing in the extrusion process, there are a lot of internal stresses in the foam. Imagine that there's a chemical reaction going on. It's a two-part process, and when it's extruded and being out through the nozzle and it's being cooled, that there's a lot of stress. What that means to you is when you start cutting a wing, it'll do a curl on you in a heartbeat depending on where you're making cuts in the foam. That's why you're going to see me using weights. Don't worry about too much weight. Too much weight's good. Too little weight, your foam will start to move on you after your first cut, and then at that point your wing's not going to be accurate when you make your second cut. Cell structure and density, the densities of the various foams generally depend upon the blowing agent used in the foam. The chemical formulation of the material itself is pretty much the same across the spectrum. But where you have variations in the foams is what we would call a blowing agent, and that's what dictates and creates the cell structure. And to kind of run through the spectrum here, I'm going to start out with the gray and the pink foams. Foamular is the name of the company, Foamular, that makes the pink foam. No one else makes the pink foam except Foamular. It's a foam that's in the neighborhood of about 1.5 pounds. It's a nice light foam. The one thing about it, the plus is that it's light. The minus is that it is a very slick, smooth foam when you cut it, which can be a negative when it comes to bonding, gluing your skins to that foam. That's one thing to watch out about, because keep in mind the wing's only going to be as strong as the skin attached to the foam. Foamular. Dow makes a gray board, which is in density similar to your pink foam. That's the one that Dow makes that's comparable. Foamular is only made back east. There are a few distributors out here. I'd say it's not worth the trouble, but if you want pink foam, that's okay. Generally, one other. All right, let's get into the Dow foams. There is a white foam that's an extruded foam. This is used in the art industry to make signs and whatever in the art industry. But once again, now we're getting into our 2-pound foams. But you can get a white foam if for some reason you want to bag a thin fiberglass in and have it white and not have to finish it or whatever. That is, to my knowledge, the only white extruded foam. It's called artboard at the Dow distributor. So then we get into the blue foam. We're going to run a spectrum here of square edge. That's what they call it, square edge. It's used in of course, all this is used in the building industry, and it's what you typically see on the outside or inside of a house for insulation. That's square edge. Once again, this foam similar to the pink and the gray foams, and this white foam, when you cut it's going to be very smooth, and so you need to go through some step that I'm sure Joe will get into regarding making that foam better friendly to your adhesive. From there, then, you go into denser foams.
The square edge is like 1 pound.
No, it's 2 pounds.
It's 2 pounds.
Yeah, generically, your blue foams that you are most available to you are 2-pound foams. From the square edge, we would go to what is called a PRB, plaster ready board. 2-pound foam, but afterwards you can look at this, you'll see that the cell structure is much more open, much more aggressive, same weight. So what happened there? How can it, if the cells are bigger, the air cells are bigger, and it's the same, what happens is it's basically the same amount of material there, but the blowing agent causes larger cells to be created. Thereby, that gives you a better surface for your epoxies or your adhesives to grab onto. So that's the PRB. A similar material that's a little harder to get is called flotation billet. Flotation billet comes in sizes, it's about 8 by 16 by 108. And it's used what it's called for flotation purposes. The cell structure is very similar to PRB. It's an open cell structure. And would work fine for where you're really trying to optimize your bonding. So that would be the flotation billet. Then as you go up into the spectrum, to the opposite end, there's a material called HI 115. The 115 designating that it's 115 PSI foam. You can build killer wings with this stuff. 6-pound foam. So if it's a slope ship or a plane where you're looking for maximum strength, have a feel of this and imagine how that would be. Glass bags or with the skins of your choice on it. HI 115. The foams that we spoke of here range in densities from. Now let me talk about compression strength. The square edge is 25 psi. That's at the bottom end of their spectrum. Then as you get into the 3 materials I'm going to describe, there's what they call a high load 40, a high load 60, and then the HI 115. And as you may guess, the PSI is a part of that designation. The 40 being 40 PSI, the 60 being 60, and the HI 115 is 115 PSI. Keep in mind when you're building wings, it's like the honeycomb structure. It's compressive strength that's going to give you that translates into the bending strength of that wing and the load carrying capability. So depending on what you're building, really the denser the foam, the better shear strength. Generally, that's not the route you're going. You want to build light for your particular purposes. Beyond the urethanes, and we've pretty well covered basically every styrene that's available. The other classification of foams that are available are the urethane foams. Now that is a 2-part system. You've probably seen the cans that you can mix and squirt in the wall and stop up around your plumbing and whatever. Well, that's a 2-part material. It's a urethane, and it has pluses and minuses. Number one, it can be hot wire cut. It's not smart to do that because it gives off gases that are not good for you. It's hard for me to get any data on that. It seems the manufacturers really want to skirt that issue. There are stories that, remember the BART tonal accident up in San Francisco? One big problem in aircraft and in mass transit a few years ago was of all the urethane cushions in those vehicles. And at the right temperature, you're basically dealing with cyanide gas, and it's really not good for you. So a lot of people died in the aircraft industry. There have been standards for a long time on flying retard standards. But particularly, so urethanes are bad news there. So my recommendation on urethane is officially stay away from it, but let's talk about it. It can be cut. It cannot be cut generally with just a hot wire. It has to be cut with a combination mechanical and heat. So you have basically an oscillating, abrasive wire that is at a temperature less than required for styrofoam. So you can cut urethane. I don't know why you want to do it. Maybe one reason you want to do it is you can use polyester resins. The urethane is very chemical resistant. So if you are a dyed-in-wool, say you're allergic to epoxies, and you wanted to get into this, then you could use the polyesters and it will not affect the material. If you get into shaping or sanding this, boy, it's miserable stuff. It makes a fine dust that just absolutely loves your eyes and every little pore in your body. So it's workable. You can use it. About the only reason you'd want to is that because it is chemical resistant. But beyond that, it's not worth trying to cut. Hot wire. Excuse me?
Weight.
The weight commercially available, interesting, is similar to the other. It goes up to 6 pounds. There are specialty companies that make urethanes for tooling purposes, and in those situations it goes on up 20 pounds. It goes way on up for tooling purposes. But commercially available, 6 pounds max. And this gets pretty light. It gets down to 1.5 pounds in that area. Yes, sir.
What's the Jordan Roracell?
Roracell, the questions regarding Roracell. Roracell is a high-performance foam that is not part of my presentation, but it's a very good question. If you're in a high-performance situation building spars or hollow core construction for wings, it's very consistent, very expensive, but it is a good substitute. Don't tell Mike I said this, but a better substitute for balks in some of those applications because of the physical and chemical consistencies in the Roracell where you have variations in the balsa. It's not hot wire cuttable. Can it be cut by oscillating wire? I really don't know that. That's a very good question. Generally, it machines beautifully. It routes beautifully. It works better than wood. So that would pretty much cover the Roracell.
Roger.
Yes.
What's the spelling on Roracell?
What is it? R-H-O? R-H-O-R?
R-O-H.
That's pretty close. Roracell. Let's talk about the old way that we used to cut foam. And I say old way, guys. I don't mean to get the right wire. There's a lot of differences in wires that we'll talk about. But you just mainly need to stretch a wire and heat it up a little higher than boiling. 225 is a good temperature. And you pull it through there, and you get a wing, and you can sand off the dingleberries and cover it up with balsa, and you got a foam core that you could use for a wing. That's the one-person process. The results aren't quite what we would like to get, particularly so when you get into high tapers. That's where the hand is not the best tool for cutting foam. Interesting, beyond that, we had some smart guys like Bert Rutan. A few years ago, 1979, I bought plans for the Lone Easy, which are still in their envelope. But it's interesting. That's why I'm here, maybe, guys, because I never built it. Bert Rutan probably is the guy who made foam cutting and airplanes kind of a synonymous term. There are a lot of guys playing around with this, and I say playing around very serious about it before Bert, but he's the guy who got all the publicity and really brought it to the forefront. And as you notice here, I call this the husband and wife, are a great way to get a divorce, okay? You see all these numbers numbered over the top of the airfoil and across the bottom of the airfoil. What's happening there is those are station lines. And what you do is on Saturday morning, you get your wife out of bed, and she's on one end of the boat, unhappy I might add, and you're on the other end of the boat, and you're yelling numbers at her, and she's got to slow up and speed up to stay in sequence with you. Not a pretty scene. I don't recommend it. Maybe that's why Bert's not building these airplanes any longer. He says liability. Yeah, liability with the wives. Anyway. But I drug these out. It's really interesting to look at these, because he even gets into some internal details in some of the cutouts. And boy, these numbers, they just go crazy here. I mean, not my wife, no. So there had to be a better way. Not bad if you've got a real good friend. It seems that I'm usually shy of friends on Saturday mornings. Roracell, R-O-H-A-C-E-L-L, Roracell. Thank you very much. So from the one man to the husband and wife, there were some systems developed. Some folks, some bright folks, said, hey, got to be a better way to do this. One unit that was on the market a few years ago was a 2-wire system and had some real clever basics to it, but it also created some problems. One of the things when you're tracking a hot wire over template is you want to keep the down pressure as light as possible. Because no matter how smooth your template is, under enough pressure, that wire can chatter. Anytime a wire hesitates, stops, chatters, you've burnt a groove down your foam core. In the mechanical design of this 2-wire cutter, that was one of the big problems. There was no way to adjust the down weights, and you would get chatter. In fact, my son, we were watching the video, and my son, by the way, is going into music now, and he sat there that night and he said, Dad, what's that banjo I hear? And we watched the video again, and what was happening was the wire, as it traversed across the template, was pressing down so hard it would go boing, boing. And this is a video I spent $29 for, so I was getting a little banjo music. So it impressed on me the fact that in a foam cutting system, you want as little down pressure on the template as possible. Trailing edge burnout, imagine this. We've got 2 wires at 225 degrees Fahrenheit, both arriving at the trailing edge, just gobbling foam like crazy. You don't get trailing edges. Sure, if you're putting bolts at trailing edges, it's not a problem. But typically, with the finesse you guys are looking for, that's not what you want. The other problem was this was using timing belts, timing pulleys, and you were limited. I'd design a wing, and invariably I'd go down to cut, wrong ratio. And you'd say, well, so the wire doesn't exit exactly parallel. We're in this for the finesse, I really believe, a lot of the guys. So you're very limited in ratios in that system, and also tapers were also very limited. When you've got a taper wing, keep in mind you want the wire to start parallel, you want it to exit parallel, so that the airfoil, the tip and root airfoil, is properly integrated down the length of that wing. In the 2-wire system that he had when you got into severe tapers, it would start off parallel, but he required that you have a dowel along the trailing edge so it would exit kind of on a strange angle to that trailing edge, and you would not get a good integrated airfoil from one end to the other. The other thing was the fact that it required a permanent installation. And the only reason I'm bringing this up is in no way is this criticism, because I think in any industry there are evolutionary, probably more evolutionary than revolutionary steps. The point is that when we started to design our system, we went out and looked at all the various ways, and we hoped we had learned something at that point. What we felt we had learned was that in order to cut good accurate foam core, you need the right equipment, and that in fact it's really worth that effort. I think in a one sentence that's the crux. It is worth the effort. So at that point we just needed the right system to do it. It became very obvious that you would like to, with the criteria of the wire starting parallel, exiting parallel, that there needed to be some type of a proportional system. Once again, there were a couple other systems that had been written up in the magazines with frames folding down, with things moving, and bungee cords. I think maybe this is where bungee jumping started. Joe Wirtz can relate to this. Bungee cords from the ceiling to carry the weight of the bow. Remember, you want to keep the wire tension down on the templates, or very light on the templates. So there were systems, and I have to tell you, I'm sure there are a lot of good foam cores that came out of those. But the thing that we were looking for was Joe Blow. In fact, I'm very fortunate in the fact that I am an industrial designer and an engineer, and that's what I've done all my life, is design products. So when you start out to design a product, you start with a clean piece of paper, and you try to set down the criterion of the marketplace, the user, and what you're trying to accomplish. We said that, first line, this had to be an inexperienced young man who lived in an apartment with his divorced mother. And in an LA apartment where it's very small. So this had to work on a kitchen counter. It had to be simple. It had to be portable. It had to be something that he could use and get it hidden in its mailing tube before his mother got home. So with that kind of a first line criterion, we dove off into designing the feather cut. In a minute, when I start to set up feather cut, I will go through each of the attributes and the things that we did come up with. But in preparation of that, so that from there we'll go right into foam cutting. I want to talk about templates. The common way to build templates, which is the logical way, is to build one airfoil template, which is a representation, a replica of the airfoil, giving you the top surface and the bottom surface. And that's fine. In the system that I related to earlier, that's the template they used, and in that instance, the foam block with the two-wire system was floating in the air and pulled through the two wires. One problem there, remember we just talked about internal stress on this foam? You can buy foam and the sheet will have a whoop-de-doo in it, and imagine trying to pull that sheet that's got a curve through it through two straight wires. Your core will be straight, but your blocks aren't. So now you come back and use that as a clamping bed on a level table and weight that down. Now your block is straight and your wing core has a curve to it. So So what we want to do is put that down on the table and not move it. Well, if you think about a system where the hot wire is always going to be pushing down towards the table, then you say, wait a minute, we can't use a single template design for this system. So what we did is we moved to the dual template system, and the template that cuts the upper contour is what let's call, for terminology, a male configuration. And the one that cuts the bottom is a female configuration, because keep in mind the wire is always pushing down. So that's kind of the description of the dual template system. When you build those templates, get a couple here to show you. What you want to do is, here's the top template, and then here's your bottom template. And when you make those two templates, what you do is you put them together. By the way, you want to design those in such a way that it will be resting on the table when it's plugged into the foam, and I'll show you that. But what you definitely want to do is match drill two holes in the templates the size of a pop rivet. Makes a good pin to hold it onto the foam. So you drill a couple of holes. You don't need 3 or 4 or 5 holes. Just a couple is enough to hold it onto the foam blocks. So your template, the heart of the system is really the template and the accuracy of the template. To talk about the template material for a minute, don't waste your time with plywood, G10 glass, aluminum, whatever. Two good materials. One material we sell and the other is Formica. Basically, our material, which we sell as a convenience item, is similar to Formica, but it does not have the brittle melamine face on it. This material here is rough on both sides, and without the shiny melamine surface, when you're bandsaw cutting this, it cuts much better, and you don't get the cracking and the breaking. Now, what you're going to do is you're going to come up with your airfoil design, and you're going to contact cement that to the sheet of the material that you use, and then you're going to, the way we build these templates, I run them through a bandsaw, and I'm off maybe a 32nd to a 16th away from my final line. And then I'll take that and I'll hold it on the edge of a workbench with the edge sticking out, and I'll take one of those hard rubber 3M sanding blocks, a little curve, a little square block. I'll put 80 grit paper in there. I'm telling you, it doesn't take long to build templates. People say, gosh, I don't want to build templates. It's really not bad. 80 grit, and in a vertical motion, I take that 80 grit and I take it right down to the line in a heartbeat. You see we've got a negative curve? On those sanding blocks, put a piece of sanding paper in the top, the curved side, and a piece of 80 grit in the bottom. So now you got a curved sanding block, put that on the edge of your workbench, and with the curved side, hog it out your negative curves there. So now we're down to the line. Then the trick, take a piece of like 220, a piece of 220 that's going to be about 4 inches by 2 inches, fold it, put it in the palm of your hand, and what you want to do, you want to sand as hard and make it as hot as possible to the point that it burns you. And now we're talking about 220, 320 max. And if you'll do that, you'll get a finish that you don't, in fact, my routine is I don't even bother to look at it. I just drag my fingernail along the edge of that. You're ready to go. None of this 600, none of this wax, none of this Teflon tape. It's just totally unnecessary. Build templates very fast. One little side item to clear away with is cutting strange shapes. And I'll get into this so that we can kind of set that aside, because
What's the template material called?
our template material is called Tri-T. Yeah, Tri-T. You can use Formica or our material. By the way, temperature, let me tell you something interesting. We ran temperature tests on our material and against the paper phenolics and the glass phenolics and the G10 glass and the whatever, and temperature resistance. This is the best. You can go away and leave the feather cut sitting there cutting or idling after it makes it cut for 30 minutes, an hour, and it will not burn this material, which is kind of nice if the phone rings, and you'll see how feather cut, when I set it up, how you can go away and really leave it unattended if the phone does ring. If you want to get into cutting out landing gear or strange things into your wing, this is probably one of the best ways to do it. A piece of coat hanger into a soldering gun like this. This will get up to about 240 degrees, and then it's just a matter of pulling it through using a guide or a template or a piece of straight wood or whatever. So just kind of to set that aside so we can concentrate on our wing cutting. That's a question that always comes up. That's probably about the simplest way to do your specialty cuts.
I got a question.
Yes, sir. Question?
What's a good way of cutting in a trough or down your wing or wire?
The way we do it is, I will take, it just happens I'll take one of my feather cut extrusions, and I will make a trolley. And this is primarily in a production environment. I'll make a little trolley that will slide down that extrusion. I'll have a string, a pulley, and a weight, and I'll set up a fixture to put the foam cores in. And in that little wooden trolley, I have a bent wire. Okay? And then as the weight drops around the pulley, it'll pull it through. It's unattended. And in those situations, because of the voltage required with whatever wire you're using, you need to get into variacs and other equipment. One note that while it's on my mind, be careful, guys, if you're using variacs. As you well know, that dial on there shows from 0 to 120 volts. All you need to be doing is standing on a wet floor and have a kid come up and crank that up to 120. You've got a real problem there. So be careful if you're just cutting with variacs. You need to use step-down transformers. We'll talk about our power supply here that does have isolation transformers.
Even with the variac, you have to make sure that it's properly grounded, because if you don't, you'll have, with a 10-volt range on it, you'll have one side at 110 and the other side at 100, and you will discover that very soon if you touch it, as Roger mentioned.
Yeah, Don Edberg there is pointing out that you really need to know what you're doing is probably the operative word there. Just be careful. It's a tempting way to go because some of you have those sitting around, but we're here to be safe, right, guys? To run through, now we're going to go into the feather cut part of the session here, and to kind of run down some of the criteria that's going to become self-evident as you see me set this up. Feather cut was designed for simplicity, convenience, portability, accuracy, and the versatility that it will give you in the various wing cuts that you may want to get into. Keep in mind it was designed on a clean piece of paper. Everything right down to speccing the wire we use, the power supplies, all the mechanics was originated on a clean piece of paper. And I think that's probably one of the advantages and one reason that it comes off as a system and gives you good cuts. To run down some of the features, you're going to see that it'll give you any ratio. Now, you may not want to cut any ratio, but maybe you do, and I'll show you. You say, well, wait a minute, you can't cut a 0, or, say if you've got a wing 10-inch root, you would never have it at 0. Yeah, you would, and I'll show you on some single point cutting, which is a great technique that works with feather cut. You'll see that it's very compact. You'll see me get a black tube out, and I'm going to pull a feather cut out of the tube. Remember the kid that's got to hide it before his mother gets home? We wanted a system so that when you're finished, you can unfold it, unhook everything, drop it in a mailing tube, standing up in a corner. I've stumbled over so darn many bows in my life that it just had to be part of it. It doesn't require a special work surface. All it requires is an edge of the table. I have a dining table at home that, when my wife's away, but dining table, great table. I mean, it's a butcher block, and I love it. Hanging on the edge of the table, and all you need are a couple pieces of tape. You'll see me do that. But you do need a smooth area for the boat to ride on. talk about a little theory that will become self-evident here. The bow, you'll notice, is lying horizontal on the table. The bulk of the weight of the bow is carried by a roller under the bow. Keep in mind, we want to keep the weight to a minimum on the wire. You'll see balance weights that I'll point out. These are little weights you can slide on the arms to adjust the amount of down weight. If you want to, imagine you're climbing up the leading edge of a wing. You want very little weight on that wire. But imagine you're making a negative Phillips entry cut, and because of the mechanics here, it's going to tend to pull it away from the template. You need a little more weight in that instance. The bows range from 24 or 28 to 52 inches. I recommend that you always use the shortest bow that'll do your job. And you always ultimately want to get into rudders and stabilizers. So our feather cut system comes standard with a 28-inch bow, and then depending on your particular needs, buy the shortest one that'll do your job, and that would be either a 40 or a 52-inch bow. A 50, when I say 28, 40, and 52, it's designed for 24, 36, 48-inch material. But if you're doing straight cuts or simple cuts where you don't get into swinging the unit a lot, then you can push it on up closer to the nomenclature description of it being 28, 40, and 52. You can set it up to do dual and single point cuts, and that's kind of interesting, and I'll show you about that. The thermal generator that we have is this unit does have an isolation transformer, and it is an AC output. Now, I'm going to tell you what guys have told me. Now, this can't quite be the truth, but it's not too far from the truth, because I've literally thrown away garbage cans of foam. I mean, if you've done a lot of foam cutting the old way, you've done it too. I've had guys tell me at the trade shows that I've saved enough money with my foam to pay for the power supply. That might have been before I raised my price. But what this does is, once you clip on to the cutting wires, at that point, you just flip on the master switch and you turn a knob until this needle centers, and that's automatically calibrated to give you 225 degrees Fahrenheit at the wire. Now, it's obviously calibrated for our wire, and that's one of the cautions that when we sell the unit, we remind you that you don't want to be putting nichrome and other wires in there. What we found out with the wires was that nichrome has a lot of thermal expansion. It's the one that's so very, very popular, and it's kind of generic when it comes to cutting foam. But we found out that there were other formulations, and we got with a wire manufacturer to work on this, that would give you less thermal expansion. Our wire is 20% higher tensile than music wire. It's a high carbon wire, and it's 18 thousandths of an inch in diameter, and it gives you a very, very fine cut. The only precaution would be maybe in Alaska, the Houston guy. Yeah, in Houston, because of the humidity, it's a steel wire. You might want to wipe it down with some oil afterwards. I've never broken a wire from use. Over maybe brain failure, and I turn on the power supply and it's too hot and I'll burn it in too. But it's always a good idea to have a few extra little spools in your workbench, just in case something, if you drop it or if you kink the wire, you can break it. But the wire doesn't wear out, and I feel like I've cut more foam than anybody in this world sometimes. But it gives you a very, very clean cut, and we get nice uniform temperature across that wire. One little characteristic I want you to be thinking about, and I'll get into a little bit later. Keep in mind the mechanics that's going on when you cut foam. You've got a wire that's at 225 degrees, and basically it's in that foam, and when it's cutting through the foam, there is a cylinder, if you would, of melted foam around that wire. Now imagine if it's in this molten medium that there would be very little resistance against that wire, resisting going through the foam, and that's very true. And you're going to see that with feather cut, it doesn't take a lot of weight to pull it through. In fact, you don't want a lot of weight. If you put a lot of weight, you're going to get a lot of wire lag, and that's one of the no-nos that we try to minimize. So keep in mind, just kind of visualize that you're pulling this wire almost through water or butter. Visualize it like that. In fact, I've seen some instances where, when you pull a rope or hold it out in the air, pull it through water, it'll whip with you. I've seen whipping in the foam, literally, with some of the setups, improper setups. So you want to be thinking about the fact that you want the wire to move through slowly, that you're controlling it by temperature and not by the weight pulling it through.
What is the speed?
Well, it depends on your patience, I guess, is a good way to put that. You probably want to run about 4 inches a minute. Pick a number. You're going to see that generally people like to cut too fast. Start real slow and then work it up, and then you'll begin to see reasons why you don't want to cut it that fast. The other thing I want you to keep in mind that's we'll touch on is the fact that when you're cutting a taper, one of the difficulties with cutting a taper is that the wire is moving very, very much slower at the tip. For example, it can be moving a third the speed, 30% taper. In that instance, there's very little resistance against that wire. There's more molten foam around that wire. It's sitting there dumping 3 times as much heat into a unit volume of foam. So the wire there will want to wander, and I'll show you what will happen there. In that instance, there's a device, we call it a safe foam device, that will hold that part of the bow back and give you a little resistance, because at the small end of the taper down here, with very little resistance to that wire because it's moving so slow, it'll want to wander a little bit, and we'll get into these details. So at this point, I'm going to dive off into cutting foam. And as we move along here, the things that I've talked about, you'll see, and I'll give you a few pointers as we go along. The first thing that we do is, and by the way, you'll notice I'm going to start from ground zero. I haven't set up anything, and I did that on purpose because I think it's very important, and somebody's going to have to watch the time for me. I think it's very important that you see how convenient foam cutting can be. First thing I'm going to do is blank the foam. That's the first question. Well, how do you make those templates when you're going to blank your foam? And how do you go about doing that? Well, the way I go about doing it is I get out my feather cut, my handy bow here, and you notice it's as if it came out of the mailing tube. Mom just left for work. I just pulled the kitchen table out here, and we're going to cut some quick foam. So you notice the wires, the way we've designed the bow, they're brass caps that the hot wire is attached to. We swing the arms out. These are spring steel rods that are isolated with Delrin bushings. Keep in mind that this part of the circuit has to be isolated. So you just pop that cap on and come over here and you pop that cap on and we're ready to run. So we've made our connections, we've got our power supply, and it's off. So we just need to plug in. And all I need to do is turn the yeah, good, thanks. All I need to do is turn the power on, and I'll center my needle, and the wire's heating up to 225 degrees. Who's going to catch the wire? Well, I know about when it's ready, and I'll get ready to grab it here. So there's your foam core. Pretty simple. Do it. Feather cut. Pull it out of the mailing tube, and we're going to need a couple of pieces of tape and my nice butcher block table here. And I'll get rid of this bow for the moment. You see that this the main body extrusion is an angle. It has we're going to hang it on the table, so this upper angle is hanging on the table. Two pieces of tape. You'll notice these pulleys that are adjustable, and we'll set those up as we're ready to make our cut. The The first cut that we're going to do, I'm going to show you a little trick. This is one of our production jigs that we have. Remember, if you're just going to do 1 core or 2 cores or whatever, build your templates like so. And just a word about building templates that there have been some questions about. For those of you who are running computers, there are some great airfoil programs on the market. This happens to be a program that we're marketing. It's called CompuFoil. And I'll just give you a few highlights that in this. It runs off of a PC. This can give you information of, it can calculate the area, the surface area of the wing, the volume of the particular core that you've cut. You can mix upper and lower airfoils. There's a CAD editor in this program. So if you want to go in and change the leading edge or the nose of the airfoil and make some alterations, you can go in and move the points that the spline line is attached to. There's a word processor, a notepad. So when you make a special airfoil, you can go in and make your notations. It's a great program. And what you then simply do, and by the way, it comes with a library of the popular airfoils, both power and glider. And at that point, you just print it out to your printer, and that's, as you can vaguely see, that's what this is here. That's CompuFoil. So rather than show you with the templates there, we're going to cut our first core with a production fixture. And what we've done here is that, you see the bottom templates? They're mounted to a piece of, in this case, MDF, plywood, whatever. And those stay all the time. You're going to make your bottom cut, and you're going to start at your leading edge and exit the trailing edge. After you've made the bottom cut, you'll flip up your templates and make your top cut. And you can see in a production environment that would be well worth the effort to do. Now this is a bow. As I mentioned to you, remember there's a roller under the back side of the bow to carry the weight. And let me assemble this one up. Actually, the other bow would, each bow would work fine, but the other bow just happened not to have a roller under it, so we do need the roller. And you notice the balance, the balance weights here. You'll notice how we will run those back and forward if I don't forget it. I need somebody on the front row reminding me to do that. Okay, so we've got our bow ready to go. 28-inch bow that does come with feather cut, yes. And then keep in mind one thing, if you want to build a long wing with a short bow, make 2 panels. You know, the foam, other thing to keep in mind, the foam, there's really very little strength per se. The foam is basically holding the skins parallel, and sure, the compressive strength plays into that. But it's no problem to glue pieces of foam together. If you want to cut 2 and then... Well, we go, the question is how long can your bow go before you have serious lag? In our instance, we're at 52 inches, and you'll get about a 1/4 inch, which is, you can't measure that effect on the foam core itself. It's very, very little. The trick now is that, by the way, I should have, when I was holding that up, you could have seen that it's a tapered core that we're going to cut here. And the thing is that we want to figure out what % taper. Now, we need to be a little careful with nomenclature. To talk taper, let's say we've got a wing that we want to build, and it's 10 inches at the root, and it's 5 inches at the tip. Now, if it's a 48-inch panel, there's very little slope. I think slope, we like to use the term slope rather than taper. You see there's very little slope between my fingers from left to right. But imagine that was a wingtip. Still 10 5 inches. You see the slope difference? That's what you're dealing with. So be a little careful. It might be a good term to get accustomed to using slope instead of taper. And if I use taper, stop me, because it should be slope. Well, we've got to figure that out. The easy way is to take your masking tape. And what we're going to do is put the masking tape down under where we're going to clip. We don't care what the root is, and we don't care what the tip is on this airfoil. All we care is how far does the pull cord have to travel, right? If the pull cord is traveling the right distance and the right speed, then it's going to start parallel, it's going to exit parallel. And it doesn't care what the root and tip cord is. Certainly the root and tip cord affects it, but as I go through the steps here, you're going to see how we very simply figure that out. My root is from where you're sitting. The root is on the right-hand side. Okay? So what I'm going to do, I'm going to clip the first pull cord. I'm going to adjust the pulley so that that will pull parallel to the end of the core. And then I'm going to clip that pull cord to the 100% mark on the swing arm. Now this swing arm here is calibrated, and it's not inches or anything, it's just a proportional calibration from 0 to 100 at the end. And we're always going to assume that the root of the airfoil is 100%. That'll be our reference. So the first thing I do is I'm going to set my pulley system up so that the cord drops down to 100%. And then we'll do our calculations based on that. Be sure you put your weights on. Drop your template so we can start with our bottom cut first. And I'm going to take my bow and I'm going to lay it up along the leading edge of the foam core. And we'll take my pin and I'm going to look down. In fact, first let me go ahead and hook this cord because I'll use this as a reference. This cord comes straight out parallel to the tip end. Okay. So I have the bow, so the hot wire is along the leading edge of the wing. And I'm going to look down vertically, and I'm going to make a mark right under that alligator clip. And that's where we're going to start our cut. By the way, the one reason you want to put your clips way out, even if you were cutting a short core and your bow is so long, the further out you are, and this is in contrary to my manual, we're upgrading that. The further out you are, you have more mechanical control, is probably the best way to put it. More mechanical advantage, more mechanical control, and you'll get a better control over your cut. I've got the first marks, now I'm going to take my bow, and really this is just serving as a straight edge is what it's doing. You could literally take a straight edge, and I'm going to make me a mark there, and I'm going to make me a mark here. That's where we want this to end up. So I'll put my bow back. And by the way, because I do tend to forget this, the first cut we're going to make is a bottom side cut. It's traveling down the Phillips entry, particularly important if it's a power wing, it's a big thick wing where you're traveling down. I'm going to slide these balance weights forward to make sure that it'll track down that Phillips entry. I'm then going to take my ruler and my handy dandy calculator. Remember, you always want to divide the small by the large. Divide the tip by the root. And so I'm going to measure this, and ideally you'd like to work in decimals, but I'll ballpark that. That's about, that's going to be about 7.9. That's right. Divide tip by the root. Did I say it right, guys? Yes. Yeah. Tip. I'm measuring the tip first. 7.9. And I'm going to divide that by this distance. Keep in mind, it's not the tip or the root cord. It's the distance that the alligator clip's going to travel. Would be a better way to put that. So this one is coming out at 9.1. We'll use those. I'm using a fraction scale, and I'm ballparking a little bit. We're going to divide that by 9.1. That's 87%. Okay? Let's see how close we come. That's the easy way to do that, though. So I said 87%. So I'm going to come over now, and I'm going to select, move the roller to approximately 87% so I can drop my pull cord down. So 81, 2, 3, 4, 5, 6, 7. So we're clipped on. Now one thing that's very important is that once you put your weight on, and this is all that moves it through, 1 pound. The weight location is not terribly critical. Remember what I said? It's temperature that's a lot more critical than the weight. You want just enough weight to move it. What I'm going to do now is grab the bow at the center point, and I'm going to pull it back and take the tension off of the front of the foam. And I notice that it's a little tighter there than over there. It's pulled up against the foam. So I'm going to make the root cord a tad longer, and I'll pull it again.
You're just testing tension?
Yeah, I'm testing to see if the wire is parallel to the leading edge of the foam core. Is what I'm doing. And I'm pulling it off a little bit and seeing which end leaves first, and then I adjust the pull cords accordingly. So we're doing pretty good there. Now to test our percentage, maybe my calculator doesn't work, right? Maybe my batteries are dead. So what we're going to do here is I will let the weight pull the bow through. And we popped off of a roller there because of the height. And as that pulls that through, well, I tell you, that's close enough for government work. That we want to cut. And we have a bow out here. Here's the wire of the bow and the spring arms and the body of the bow. And there is a roller under here. Draw an imaginary line and get an apex. Okay? What you ideally want to do, so things don't run into each other as the bow is swinging through, is you want to, and I'll use my elbow there, you want to swing an arc around that point. Okay? What you want to do is turn the wheel, and it's adjustable under there. You turn the wheel so the axle of the wheel is a center line that intersects this apex. Okay, think about that. If the wheel is set with that axle apexing, now it's going to swing in an arc. That's one thing, just mechanically, that you want it to do so it doesn't go strange. The other thing is, remember I told you that at the tip end, if this is, say, 30%, we're calling that always 100%, the wire there is dumping 3 times as much heat into the foam, right? A bunch more molten foam there. What happens is, this wire will tend to slip towards the area of least resistance. And so your bow, you could cut this, if the roller was just pointed straight ahead, this would tend to slide towards the tip. So to go through everything, the roller, the weights, the pulleys are clear, our weight is ready to go to pull through, and what I'm going to do is I turn my knob off, I turn my master now on, and I then center. Now,
Why'd you select 60 on the weight?
let me make one point. Do that on the bow. As the foam is heating up, the residual foam, it goes through a transitional temperature that turns it into a good glue, a good adhesive. And for an instant, that wire can bond itself to the template. Sometimes it'll break, most times it'll break loose, sometimes it'll sit there while you're off getting your Coke or your cup of coffee, and it'll burn a groove down the leading edge. So it's a good idea just to kind of ding the bow there. Now, if I'd projected the leading and trailing edge out to that apex, remember, and the axle of the wheel is correct, that bow should just track parallel through the foam cord.
All you did was tap the bow there.
Yeah, just tap a little vibration. Yeah, you just want to make sure as it goes, ramps through that particular temperature, that it's not going to do anything strange.
That's how you started it, and turn on the heat.
The way I started it, I turned my master switch on. I turned my master switch on. I turned the knob until the needle's centered and the thermal generator is pre-calibrated with 225 degrees Fahrenheit. That I didn't do, and in this age of wanting to be safe, what can happen is, remember I told you about one end of the, when you're cutting a severe taper and you got a lot of molten foam there and little resistance, that the end of, let's say if we were cutting a severe, this is dropping down to a very 30% or whatever there on our slope, the bow will, the pull cord will want to just kind of hunt and seek, and it can give you some strange detail on your foam. So in this day and age, and if this becomes a little bit of a sensitive subject here, what we do is we want to be a participant of safe foam. So what I do is I always carry in my billfold, and the funny thing is it leaves this little circle here that my wife always asks me about. And by the way, is there a trash can around here? What you always want to have with you are your rubber bands. Never leave home without them for safe foam cutting. What you're going to do on the tip end, you're going to take that rubber band and you're going to put a little tension on it. Now what that'll do is at the end of the end that wants to hunt and seek, because it has very little resistance, it'll put a little back pressure on it. So let's finish this cut real quick with minimum verbiage and get on to the one that's stranger than fiction. So I flip up my templates. You saw me slide my weights back. The wire is cool, obviously, so I reach here and I push down to make sure the wire is on the template. It's a good habit to get into. Our pulleys are clear. Our pull cord's clear. And the rubber band, we need that in both instances because it can still hunt and seek if it was a severe taper. That would run you nuts without your rubber band. So in that instance, we were already calibrated, so all I have to do is turn the power supply back on, and it's ready to cut, and it's heating up, and give it a jingle, and we're underway.
Roger, what keeps the upper templates from just flopping down on the weight?
Enough friction. That's a piano hand. You're welcome to look at this afterwards. I'm going to get ready to show you the stranger than fiction here. Yes, sir. There are ramps on the templates. Oh yeah, definitely have ramps. I use 3/4 of an inch. Pick a number. So we've made our cut. Whenever you want to come back from answering the telephone, you just flip her off. And what I'm going to do is I'll show you the cut that we get. Okay? We're going to cut a wing, and we're going to cut a wing tip, and it's all going to be one piece. And we're going to call it elliptical, which is kind of a nice word. An elliptical wingtip. Whoa! You see what I'm doing? I'm taking my foam core and I'm spacing it up 3/4 of an inch. I'm taking another board that's going to lay on top. I want to hold this section of the foam straight. And I'm going to take some of my press brake dies and lay them up here because I want to keep that level. What I want to do is have a nice elliptical wingtip so we can go back and build P-38s and Jugheads and Curtiss P-40s and all those good things. So watch what I'm going to do here, guys. Aha! Ooh! I told you the admission price would be worth it, didn't it? By the way, you get what you pay for. Okay, so there we are. Now we do need a template. Now keep in mind this is a single point cut. So all we need is a template at one end, and then we need a device to hold the other end of the bow straight. And I get my famous pot rivets out that are hiding over here.
This is more common when you wouldn't have a jig. I mean, when you stick the airfoil on the end of the tube.
Yeah, I'm going to show you the way you'd normally do it. The other I was just kind of fancy and I was lazy. And so I'm going to start with the bottom template. Remember, we start at where the leading edge and go to the trailing edge. And I'm pinning the template referenced against this piece of particle board. So now this is the bottom cut, right? No, we'll call this the Hokey Hulk, okay? All right, so we've got the template set up. And what I did, this piece of foam, if I take the root and the tip and I converge it to a point, remember we're doing single point, then I know that that's 38 inches. So what I'm going to do is set up my single pivot point out here at 38 inches. Yeah, it's just to extend the leading edge, extend the trailing edge out, and where that intersects. And in this instance, it happens to be 38 inches. This is a piece of sheet metal with a groove cut in it at the appropriate height. And then what I'll do is grab my long and trusty 40-inch bow, and I'll sneak behind here. 48 inches and 38 inches makes sense, doesn't it? It's long enough that it'll reach. Now what I'm going to do is I'm going to capture one end of this bow. When you wrap the wire on the bow, you make a little knot, so it's captured now, so it can't go left or right. And I'm going to slide all this around until I align the leading edge of the foam core up with the wire. So we'll be starting out parallel, and because of the geometry, it's going to exit parallel. And I'm going to put my weight down, and I got a clip on here. Now, this is a single point pull. We don't need to worry about ratios, percentages, and all those good things. All we need to be concerned about is pulling the bow through the foam. So I'm going to clip on. I don't need to worry about percentages. I'm going to go out over here, and I'm going to clip on somewhere, which is fine. So we're clipped on, we put the weight on. Okay, let me just make sure there's no brain failure involved here. Now, remember what I said? Get the axle through the pivot point. I've turned the axle.
Push your wire back.
Push.
It's bowed up on this end. It's caught on the foam.
Something's going to happen here. He's right. The wire looks like it's way up on the foam, but that's what we want, and you're going to see why in a second. And see, the wire is a straight line back to my pivot point. That's all I care about. All right, I'm clipped on. I'm at 38 inches. We're hooked on. We got our weight. No, that's right. We do. The gentleman's right. We need to complete the circuit, but we don't need that as a pull cord. So let's see what we got here, guys. We are cutting the bottom first. We're starting at the leading edge, and it's up and running. Now, what's happening is, look at it. See that foam's bowed down. When that pops back straight, you're going to have a curve. But what's really interesting is when you look at the plan form. So hang on.
How did you select the thickness of the particle board at the top and bottom? Does that matter?
I have a garbage can full of foam in front of my house right now. I've been wanting to do this for about 1.5 years, and I figured you guys, if you're going to drive from Alaska, I better get busy. And I've got a can full of foam. No, it was just empirically. Yeah, this obviously can get a lot more scientific, but this is, for example, you could do a bow in the foam back here. Okay, there we go. We've got one, and this will only take a second, guys. Now, because this is a little cumbersome, and this will be ending the demonstration. There are other things that we can always talk about afterwards. Anybody wants to corner me. Okay, I'm going to bring the bow back. I'm going to swap my templates. And by the way, remember, we match drill the templates. So that I'll use the same holes in the foam. So there we go. We're there. Now, this time, since we're at 3/4 inches nominal, we want to go up a inch and a half. So we're up 1.5 inches. My bow is on the template. It's lined up. We're up 1.5 inches, and because the foam is now in 2 pieces, we want a little bit of weight to hold it all together. So we're up our 1.5 inches, 3/4. We're in our pulleys. We're hooked. We're ready to go. Oh, yes. Ooh, hey, very good point there. I was supposed to assign someone to remind me about the weight.
And the weight on your bow, put the balance on it.
Yeah, we're going uphill. Yeah, I know it. Let me tell you, when this came out, I was so excited. I said, this is worth it. Yeah. You haven't seen the results. Next time we get together, we'll talk about skinning and sheeting and all these other good things, guys. Where's Mike Tavey? By the way, the guy that came the next to the furthest distance gets his foam core. Who was that? Right here. All right, Denver gets. Whoop, where'd you come from? Oh, watch that guy back there.
He's still on the oldest.
Boy, I hope this works. God, I hope this works after all this. Yeah, I know. We're really in trouble. Guys, this is like having birth to twins. All right. All right.